with electrodes, salt bridges, batteries, and knowing how a battery works is, I would say, it's can be useful. We live in a society where there's batteries everywhere. Everybody here is probably carrying multiple batteries on you. I know I'm carrying two, one on my phone, one on my watch. Everything, and my laptop has a battery in it, right? Everything, for the most part, has like some kind of battery component nowadays. And batteries are relatively simple once you know how they work. What I'm gonna draw is like the most basic type of battery. And it's also something that you make in lab as well. So I'm gonna make what's called a voltaic or galvanic cell. They basically mean the same thing. They are very crude batteries. So I'm going to draw my picture and then I will label it. And then I want like a little bridge here. All right. So let me label my picture here. So on the left, I'm going to have what we call an anode. On the right, I'm going to have what we have a cathode. An anode, by definition, is where oxidation happens. A cathode, by definition, is where reduction happens. And so to kind of understand these concepts, we need to go back to General Chemistry 1 for redox reactions. And the terminology you want to remember is oil rig. An oil rig is oxidation is loss, and I like to tack on, of electrons. Reduction is gain of electrons. So for the anode, that's where oxidation is happening. So that's where electrons are leaving, and they flow towards the cathode. That's where electrons are going. Now, if we think about a battery, and in my picture, we have that flow of electrons. What you can do is right here in the center, you can put like a device. And so the electrons have to travel through that device on their way to the cathode. So we can use those electrons to power anything we want. Power a car, power a phone, power a watch. In essence, that's how a battery works, right? And this red bit, this is called a salt bridge. A salt bridge allows ions to flow. Because let's think about what's happening on a chemistry front. Electrons are going towards your cathode. That means your cathode is going to become negatively charged. Electrons are leaving your anode. Your anode is going to be positively charged. Based on your understanding of chemistry, Do you think electrons want to go to a negatively charged area? And they don't, right? Electrons are negative, so they don't want to go to a negatively charged area. So a salt bridge allows positive ions to go to the cathode and negative ions to go to the anode. So I'll write that down. So salt bridge, cations go to cathode. That's why it's called a cathode, because that's where cations go. Anions go to anode. That's why it's called an anode. This allows the battery to continue to run without stopping, because otherwise the electrons would flow until there's a charge imbalance and then they would stop. So your battery would work for like that fast and then it'll be dead. So that is fundamentally what a battery looks like. There's a little bit more I want to talk about, but any questions just about the overall image of how a battery or a galvanic cell looks like? Or any questions about that terminology? All right, let's talk about cell notation. Or, yeah, so cell notation. So I'm going to redraw a battery. In general, you always have your anode on the left and your cathode on the right. You don't have to when it comes to like this picture, but that's what people generally do. And let's say my anode right here, we have solid zinc, and my cathode is made out of copper. So when we make batteries, we generally make them out of metal. By the way, in all your devices, what is the metal you generally use as a battery? You know what metal are generally in here? Not cobalt for a battery. Does anyone remember the story of the phones like catching on fire in airplanes like 4 years ago? So one of the things about lithium batteries is that they're very reactive and they sometimes catch on fire by themselves. So it's very dangerous to transport them. Most batteries, we have some kind of lithium complex to make. But here we have zinc and we have copper. In rudimentary batteries, we're also going to have a liquid here. And I need to blow this up because that's a little too tiny for my eyes. So in our liquid, here we have zinc nitrate. And in our other liquid, we would have copper nitrate. So generally, you have solid metal that's attached to some wire. That's where the electrons flow. You have your salt bridge that allows the counter ions to flow, so both cells remain neutral. And then we have our reaction. So at the anode, is the anode being oxidized or reduced again? Ox. So a way to remember that, an ox, red cat. So the cathode is reduced The anode is oxidized. Anox red cat. So what is happening on the anode side? And again, I'll write down oil rig. So we are being oxidized. So we lose electrons. So that zinc is going to zinc aqueous. And on the other side, we are gaining electrons. So the reaction that's happening on the other side is that aqueous copper is becoming solid. And so if we were to hook this battery up for real and just let it go, what would happen is that you would see the zinc solid, the actual metal, start to shrink because it will start to go into your liquid during this reaction. The copper solid would grow. You would see it getting bigger and bigger and bigger because the copper from the liquid would go onto the metal. That's what those reactions are saying down there. Zinc solid is becoming aqueous during this reaction, so it's breaking off to go into the liquid. Copper aqueous is going to solid. It's going from the liquid to the solid. But let's talk about this idea of cell notation, which was our topic for this slide. Cell notation is basically how to write this picture in words. So write picture in words. Because if I'm writing a paper, I can't draw this in like a sentence, right? I need to write it down. And the notation is, it will be your anode, salt bridge, cathode. So your anode's always on the left. So let me write down this based on our picture. So we start with zinc solid. Oops, zinc, not the number 1. Our notation is zinc solid. And then you have a line. So this is your actual anode, the metal portion. Then you have a line, and you're going to say, what's your liquid? So my liquid is zinc nitrate. Oops, NO3, 2 aqueous. So that's one side. It's the solid line, liquid. Double line, that's saying, okay, we have a salt bridge. And then you do the opposite. You did liquid solid. So go solid, liquid, liquid, solid in this case. So copper nitrate. Then copper solid. And another way to kind of remember where everything goes is you should, like the salt bridge, it's telling what's next to the salt bridge is what the salt bridge is physically going into. Right? In my picture, my salt bridge is going into the liquids. So in my notation, I have the salt bridge next to my liquids. And then at the end, you have the actual solids. So for any battery, any galvanic cell, that is how I can write down that picture. Anode slash your liquid, double slash your liquid slash your cathode. All right. Any questions about doing cell notation for a galvanic cell? You're going to get practice with this in lab. I think today's your last lab, right? And so you're going to be doing galvanic cells. So you're gonna get fed all this stuff again in 45 minutes, those of you in lab. And so the last thing I have to teach you, even though there's more for this course, but because of almost said January 4th, July 4th, and all that this semester, and because we don't get an extra day for final exams, I have to do a class day. We have to cut off some information. So this will be the last thing I tell you. Half cell potentials. Or basically, how to calculate the energy of a galvanic cell, of a battery. And our equation is E naught cell. So the energy of a cell, the energy of a battery, is equal to the energy of your cathode minus the energy of your anode. So minus Ca. E cell equals C minus A. Cathode minus anode. And so where do we find the energy of a cathode? Where do we find the energy of an anode? Well, lucky for you, all of these are constants. And are generally provided. And so let me go to, what slide am I on? I'm on 266. So let me go to slide 266 to show you what I'm looking at. So this table, this blurry table on the right, is from your book. And what this is a list of a bunch of cells with energy values. So just to pull some out, we'll go to the top. If you had a cell made out of fluorine gas, the energy value you would use for that is like 2.87 volts. Here we have one boxed in. This is hydrogen gas. So if you're using a voltaic cell that uses hydrogen, the energy you would use for that is 0. This actually gets a specific name. Hydrogen is called the She, or the standard hydrogen electrode. So She stands for standard hydrogen electrode. Scientists decided hydrogen gets an energy of 0. And then we compare everything to hydrogen. So hydrogen gets 0. And then you'd look up whatever battery you want to make and see what are their energies to use in this equation. So let me go back to writing stuff down, because this is a lot of information on one slide. All right. So on that slide, we have an example. So the example is basically, I'm making a battery. I'm making a copper and zinc battery. And my question is, what is my anode? And what is my cathode? So what is my anode and cathode? So basically, this is one of the things you're going to be doing in lab. You're going to be making batteries out of metals like this. And you're going to be told to calculate E cell. You're going to be told to calculate the voltage of the cell. And so what you would be given is that you would be given these potentials. So you would be given, okay, if copper if copper 2 plus is reduced to copper solid, the energy of this is 0.34 volts. And for zinc, if zinc is reduced, so zinc is made into zinc solid, the energy of this is negative 0.76 volts. And as long as you are given these cell potentials, that's all the information you need to know what your cathode and what your anode. So let's do this example calculation. It's the last thing I'm going to teach you. All right. So let's say you made a guess. Let's say you said, oh, I think my copper is my cathode. Let's say you guess, okay, that would mean zinc is my anode. So let's do that calculation. E cell is equal to the energy of my cathode, 0.34, minus the energy of my anode, negative 0.76. So all you do is you literally look at this table, and depending on what's your cathode and what's your anode, you just plug in the values from that table in the correct position. And this math, I can do that in my head, I think, is 1.10 volts. All right. When you get an E cell that is positive, that means this reaction is spontaneous. So yeah, your guess was correct. If you put copper as your cathode, if you put zinc as your anode and you did that calculation, you got a positive voltage, which means, yeah, that battery will work as written. If you made the opposite guess, if you said, well, I think zinc's going to be my cathode. I think copper is going to be my anode. then you would have got a negative 1.10 volts, which means no, you have it mixed up. Basically, what you did is if you were jumping a car, you switch your wires, you put it on backwards. So yeah, when calculating E cell, you want a positive value. So just to bring it home, because we've talked about a lot of different ways. So I'll put this table up one more time. For a spontaneous reaction, delta S universe should be positive. Delta G should be negative. K should be greater than 1. And now our last piece of the puzzle, E cell, is positive, right? If you're given any four of those numbers, S universe, G, K, or E cell, you can tell me that the reaction you're looking at is spontaneous or not. Like I said, you're going to get a lot of practice calculating E cell today. So this should be rammed into you pretty well. For those of you in lab. If you're not in lab, that means you've probably taken it before, so you've seen that lab. Right. Any questions about the calculation of E cell there? Yeah. Mm-hmm.
But we're just really think it would be spontaneous.
Yeah, so let me just walk through problem 112 really quickly. So we have nickel solid plus zinc 2 plus aqueous goes to nickel 2 plus aqueous plus zinc solid. And you're given a bunch of values, right? So let's just look at, so you're given the nickel reduction potential of negative 0.23 volts. You're given the zinc reduction potential of negative 0.76. And the question is, as written, is this reaction spontaneous? All right, so we have to tie a couple pieces of information together. So for this reaction, nickel went from a charge of 0 to a charge of +2. So if you go from a charge of 0 to +2, are you oxidized or are you reduced? Oh, we have two different answers there. So if I go from 0 to +2, you lose electrons because you're becoming more positive. And oil rig says oxidation is lost. If you are oxidized, you are the anode. Right? So we are connecting all those little pieces. That means nickel is your anode. Zinc is your cathode. E cell is my initials, cathode minus anode. That's why I can remember it easily, Ca. My cathode value is negative 0.76 minus my anode value, which is negative 0.23. E cell for this reaction is negative 0.53 volts, non-spontaneous. I have written this reaction backwards. So yeah, for 1112, you have to determine what's being oxidized and what's being reduced. That's by looking at the charges. Then you just plug it into our E cell equation. If you get a positive value, it's written correctly. If you get a negative value, It's non-spontaneous. That's it. And you ignore the moles, right? And see, I have like 3 moles of silver. That does not. You just look at that symbol. Right? Any other questions about E-cell? Right. So my last announcement is that you'll have an extra credit homework. Extra credit. Wow. Oh my goodness. The caveat is that is due 8 a.m. on Thursday. It's a quick turnaround. And why is that? Because that's basically the homework of the stuff we just covered. Right. I would highly recommend you look at it at least. Because it's everything we went over today. So this is your practice. And it's due before 8 because that's the final. So there's no point in doing it after you take the final. How much is this worth? It's going to be, just add it onto your homework grade. So like if you have been missing some points there, this is a good way to recatch that up. Otherwise, bring a pencil for Thursday. And if I said Wednesday, I meant Thursday. Bring a pencil for Thursday. Bring a calculator, or I'll have calculators available. I will give you a Scantron. Is the final of the ACS or made by me? It is made by me. Yep. Any other questions before we break? Yay. Yeah, I agree. Any other questions before we break? All right, if you haven't done so already, please pick up your test. Otherwise, if you have questions from now to Thursday, feel free to email me. Your old tests should be online, so you can practice those if you want. But good luck, study hard. We'll see you Thursday morning. Maybe. And that shouldn't be too hard, but it's just, so the equations, I can tell you right now what they're going to be. Oops, wrong thing. It's going to be E-cell. I'm going to give you that. Give you those two up top.
So after this.
Oh, these two up top. I think that. Oh, this equation, delta G equals delta H minus C delta S. That equation. Yeah, that's pretty much it. Okay.
Have a good day.
You too. Yeah, I think that's probably all I would give you because everything else would have been from the previous test.
And then I understand.
Oh, yeah, the buffer equation. I'll get that to you.
That was tomorrow.
Uh,
Or